This is Dan Allford with ARC Specialties. This is another in our series on design to automate. Robotics is harder than it needs to be. Frequently, if you redesign your part or your process, you can facilitate the automation of your parts. So a lot of times we'll go to a customer and explain this to them and give them specific examples. Sometimes they adopt our techniques, sometimes they don't. There's lessons to be learned from both. This one's fairly subtle today, but I'm going to go through it and try to explain what we're doing here. So traditionally, on all the ground engaging surfaces on rock bits used to drill oil wells, they were coated with a combination of steel, that's the matrix, and tungsten carbide. You can see these large carbide particles on this part, and this is how it had been done forever. These particles are agglomerated. It's an interesting technology. The particles are actually rolled into small spheres, much like a snowball does on a hill. That's a story for another day. That means that the tungsten carbide is actually cemented together using cobalt. This is the same technology that's used in lathe tools and any tungsten carbide cutters. And it works fairly well, obviously, but the problem is there's a better way. And the other problem is traditionally they've always used large diameter carbides for this application. So our idea is we're going to go to plasma, and when you go to plasma, you can no longer run these large carbides because plasma torches simply aren't equipped to flow large carbide particles. But when we first started to automate this process for the rock bit industry, nobody believed us. And so what we had to do is we actually had to take these torches apart. We drilled out these holes and allowed us to drop these large carbide particles, which look aggressive and tough and don't work very well. And so we went to all the trouble of redesigning the torches so we could use the large particles, and then we ran G65 tests on that baseline. And it was equal to the way that it had been done with oxyacetylene and atomic hydrogen for all those years. And then we approached them with our technique. Our technique is tungsten carbide. It sounds the same, right? But it's not. This is actually macrocrystalline carbide. So these are single crystal carbide particles, WC, W2C, and so there's no cobalt. So these are actually more abrasion resistant. And we could have used a matrix of steel like we had in the past, but instead we went to a chrome nickel silicon boron matrix, much more expensive, but it has a couple of advantages. One of them, it's immune to heat treat, because these parts go through a subsequent quench and temper, and it'd be better if we didn't harden this matrix. So with chrome nickel silicon boron, it was immune to the heat treat. And then these tungsten carbide particles made out of WC, W2C were more wear resistant. But we're still back to that issue of large diameter carbides. Everybody's convinced in the industry this was what made them durable. So we're running much smaller carbides than this. Fortunately, there's a great test put out by ASTM. It's B611 and G65. It's high stress and low stress abrasion resistance. So we're able to compare the old traditional atomic hydrogen oxyacetylene applied agglomerated carbides in a steel matrix to our steel matrix agglomerated carbides, large diameter, to the new technology. And lo and behold, we were right. And not only did we have improved wear resistance, but we also facilitated the plasma welding of all of these parts. So it's all tungsten carbide, it's all in a matrix, but these subtle differences are what made the difference, and that's why these rock bits nowadays are welded with plasma, chrome nickel silicon boron matrix, and macrocrystalline carbide. Sometimes the devil's in the details. I hope this tip helps you with your next automation project.